Hey everyone, thanks for being here. March is here, and so is the pollen. We got another week of pictures and video to go over while we wait for more detailed updates on Artemis progress and status. There was another RS-25 Retrofit 3B test. We got a couple of picture dumps, a promotional video. So let's see what info we can dig out of that or not. On Monday, February 26th, Northrop Grumman announced that the workforce at their Promontory, Utah facility had completed the first motor segment of the next generation SLS solid rocket booster. A picture of the motor segment was released with the announcement, noting that this loaded segment will be fired as a part of the first full-scale development motor. That test firing at Promontory is currently scheduled for the end of this year, 2024. The next generation composite case boosters are being developed as a part of the SLS Booster Obsolescence and Life Extension program, also known as BOLE. The BOLE boosters are planned to inaugurate the SLS Block II vehicle beginning with the program's 9th launch. Northrop Grumman will be working on design, development, test, and evaluation of the boosters between now and then. Similar to the full-scale test program for the current SLS solid rocket boosters, 3 development motors and 2 qualification motors are planned. The caption for the picture also noted that the image shows the motor segment being transported to final assembly. There is a final assembly building at Promontory, which is used for final closeouts and addition of segment-specific hardware, so that was my first assumption. However, it may be euphemistically referring to final assembly of the test motor at the T97 large motor test facility on site there. I submitted a question to Northrop Grumman on Monday the 26th, asking which specific segment is shown in the picture, since that is not specified. So far, no response, so we're left to the usual waiting and wondering. I don't see a forward or aft dome, so I'm assuming that this is a center segment rather than a forward or aft segment. Assuming that the general concept of operations for production of these motors is similar to the current shuttle-based ones, the forward segment will have the igniter installed in final assembly, and the aft segment will have the nozzle installed there. Most of the calendar year is still in front of them, though, so we'll be waiting to hear more news from Promontory and Northrop Grumman. The BOLE boosters will have pretty much the same outer mold line as the existing shuttle-era steel case boosters, but they are designed specifically for SLS. In contrast, the basic design of the SLS 5-segment redesigned solid rocket motor V was completed during the short-lived Constellation program, so the central thrust profile of the current boosters was designed for a single-stick launch vehicle. The new boosters are optimized for SLS, and this latest Northrop Grumman photo release says that the new design, quote, adds nearly 5 metric tons of payload capacity, unquote, above and beyond the performance of the Block 1B vehicle. It's not stated explicitly, but presumably that is making reference to the performance of the vehicle through translunar injection, which is where the SLS mission as a launcher is essentially complete. The current Block 1 vehicle can send approximately 27 metric tons through TLI, which is basically the Crew Orion spacecraft's control mass. Block 1B, with the Exploration Upper Stage upgrade, is said to increase TLI performance up to about 38 metric tons, enough for a 10 metric ton class co-manifested payload to come along on the ride with Orion to the Moon. Cargo versions of SLS that are still being studied but not actively developed at the current time would, in theory, have a few additional metric tons of performance. The BOLE next-generation boosters eliminate the toxic hydrazine fuel used for thrust vector control, moving to the electric TVC that Northrop Grumman originally designed for its since-canceled Omega launch vehicle. The thrust trace of the BOLE motors is also designed to reduce the amount of throttling that the core stage RS-25 engines have to do. The Space Shuttle and SLS had and have throttle buckets that need to be performed to keep vehicle loads within limits. In the case of SLS with the current boosters, it has a maximum dynamic pressure throttle bucket around 1 minute into flight and a bolt bucket around SRB separation a little more than 2 minutes after liftoff. On Tuesday, February 27th, imagery of one of the exploration upper stage weld confidence articles was published on Avail, images.nasa.gov. These pictures and B-roll video were taken on December 13th last year at the Michoud Assembly Facility in New Orleans. They show the EUS liquid hydrogen tank dome weld confidence article. As noted in the story I wrote for NASAspaceflight.com in January, the Boeing folks noted that the weld confidence articles are used to certify that the weld tools at MAF are ready, in this case, to do all the welds there for EUS production. The core stage barrels and domes are different thicknesses, and the friction stir welding tools at Michoud are reconfigured to the specific parameters for a weld. The thickness varies from element to element, but the aluminum alloy used in the core stage structures is relatively uniform. In addition to its specific thickness and other parameters that factor into welding, EUS is using an aluminum lithium alloy for its structure. Most of the other welding tools at MAF are shared between core stage and EUS, but that's one of the reasons a separate dome welding tool is used for those large circumferential dome welds. This second circumferential dome welding tool, or CDWT, is also called the Universal Weld Station. Separating the core stage and EUS welding also allows more parallelism in the work schedules when assembling propellant tank structures, since each SLS build beginning with the fourth one for Artemis IV will require both stages. Removal of the LH2 tank dome from this CDWT tool in December signified that the necessary welds in that tool were complete. Eventually those welds will be tested, but first the dome will head over to the Vertical Assembly Center to certify that tool's EUS-specific welds. The VAC will be used for dome-to-barrel and L-ring-to-barrel welds with EUS structures. These are similar types of the welds performed for core stage, but with different materials and thicknesses. For comparison with EUS, the VAC performs the same dome-to-barrel and L-ring-to-barrel welds for core stage structures, but it also performs barrel-to-barrel welds for the propellant tanks. The EUS LH2 tank has the same 8.4 meter diameter dimension for its single barrel, but the much longer core stage propellant tanks both have multiple barrels. In addition to welding the two LH2 tank domes to its barrel, the VAC will weld L-rings to the forward and aft adapters and to the inner stage for EUS. Once all the VAC welds are complete on the weld confidence article pieces, similar to the liquid oxygen tank weld confidence article that was used in the certification process for other weld tools, several coupons will be cut out of the LH2 tank confidence article welds, and those will be tested before NASA and Boeing sign off on them. Getting into the VAC to perform these welds to certify the tool was delayed because the tool was occupied for a long time by the partially completed liquid oxygen tank for Core Stage 3. As noted in a recent video, issues with structural assembly of that tank meant that part of the article was stuck in the VAC from late 2022 throughout 2023 until early February of this year. The completed core stage tank finally vacated the VAC on February 1st, and the EUS LH2 tank weld confidence hardware is next in line. What we should see sometime in the future is imagery of that EUS weld confidence hardware either being loaded into the VAC and or after the welds are complete and it is being removed. Once the welds are completed, tested, and verified for the weld confidence articles, Boeing should be in a position to continue welding qualification articles and eventually assemble the structural test article. The STA was expected to be completed sometime around the middle of next year, and then it would ship to Marshall Space Flight Center in Huntsville, Alabama, for that structural test series in the 4693 test stand at the center. The eighth test in the Retrofit 3B test series for RS-25 production restart was conducted on Leap Day, Thursday, February 29th. The engine start sequence wasn't shown in the live feed this time, but the start command occurred a few seconds after 1:40 p.m. Central Time, or 1940 UTC. Engine 0525, a Space Shuttle era asset inherited by the SLS program, is a development engine being used for this test series. As the retrofit name implies, most of the engine has been retrofitted with newly built hardware by Aerojet Rocketdyne at facilities in California and Florida. RS-25 testing is conducted in the Fred Hayes test stand at Stennis Space Center, formerly the A1 test stand. For test number 8, the engine was fired for 615 seconds, and according to NASA Public Affairs, the engine was throttled between 80 and 111% power settings. As noted, the engine start sequence wasn't shown, and by the time the feed switched to camera 442, the engine had already throttled down to its 80% minimum power level. The RS-25 engine was renamed from its original Space Shuttle main engine roots, and its rated power level was 375,000 pounds thrust at sea level, or 470,000 pounds in a vacuum. That is what 100% equates to, but the SSME RS-25 was upgraded to higher thrust levels during shuttle and still higher power levels for SLS. Shuttle flew most of its launches with the 3 engines at 104 or 104.5% thrust. In the more extreme shuttle abort or contingency abort cases, the engine or engines that were still running could be throttled up to 109%. That was demonstrated on the ground in the test stand, but was never necessary in flight. SLS is now expending the RS-25s in their application as the core stage engine. The first 4 flights will run SSME hardware adapted to SLS operating conditions at 109%. Beginning with Artemis V, the newly built production restart engines will run at 111%. The engines can be throttled in 1% increments down to about 67% with the leftover shuttle hardware. For the production restart hardware being certified in the Retrofit 3B series, the minimum power level is 80%, and that happens to also be the lowest power level the engines are typically run at in the ground test stands, which are at sea level, essentially. For this test, again, there wasn't much information on test objectives, throttle profile, or test plans, but in the live stream of the test on the NASA Stennis YouTube channel, the NASA Stennis representative noted that not just the second production restart nozzle was replaced on the engine after the 6th test on January 27th, but also the low-pressure oxidizer turbopump. The representative also noted that the test team plans to complete the final 4 hot fire tests in the 12 test series in March. When the live stream was showing camera 442, we did see a few parts of the throttle profile. At around 105 seconds, the engine was throttled up from 80% to what I take to be 111%. At around 240 seconds, we saw the engine throttle down gradually from 111 to 80%. Then, around 545 seconds, we saw the engine throttle up from 80% to an intermediate power level. Looking at the mock diamond, it looks like somewhere between 90 and 100%, but it looks like less than 100%. But again, we don't have the actual numbers, so there's a little bit of guesswork in this. The shutdown command was indicated at 614.9 seconds, only a tenth of a second different from the 615 seconds advertised, and we could see the shutdown sequence with the shutdown helium purge coming on at that point. This is the last planned hot fire test series as a part of certifying the new production lines and engine upgrades for launches beginning with the 5th SLS launch, or Artemis V, as I noticed before. I went over some of the background and history of RS-25 production restart in the last video. The new flight engines should be the next ones into the test stand. They will be numbered beginning with serial number 20001. Each new engine will get a single green run test in the Fred Hayes test stand that serves as an acceptance test for the unit. I don't believe a forecast has been released yet for when the first flight engine will be fired, but hopefully that will be noted after Retrofit 3B ends later in March. Here are some other views around the A-Test complex from pre-COVID visits to Stennis Space Center. This is a view from an area between the A and B test complexes. Here we're looking at the A2 test stand in the foreground and the A1 test stand in the background. The A2 test stand was mothballed during the last decade, but has since been leased to a commercial company, Relativity Space. These are historical shots of the A2 stand, which is being converted back from a single-engine facility to a stage test stand, as it was when originally constructed during the Apollo program budget boom. In between is the Test Control Center blockhouse for the A-complex stands, both A1 and A2, although I'm not sure how that will work with different users of the test positions. Several of the visits ended up at the closer test stand viewing area for what was still known as the A1 test stand back then, now the Fred Hayes test stand. The closer viewing site makes a big difference in terms of the sound levels. The Stennis folks who would escort us around typically provided earplugs regardless of the viewing location. However, this was the one where they felt necessary, since tests typically run for 8 minutes. This particular test was in July 2018 for the short-lived AR-22 engine program, which was basically Space Shuttle main engine components left in Aerojet Rocketdyne's inventory from before SSME Block 2, or hardware that had exceeded shuttle flight time or cycle limits. These are NASA Stennis drone views from tests a few years back. They provide a better view of the barge tanks that are used to support full-duration RS-25 tests. As the NASA Stennis livestream introduction often notes, the stand has built-in run tanks that provide enough capacity to feed an RS-25 engine for about 350 seconds. For tests longer than that, the stands are equipped with interconnected piping and other infrastructure like pumps that allow the run tanks to be backfilled with additional propellant from barge tankers that are docked adjacent to the stand. The engines can fire much longer than the SLS 500 second or Shuttle 520 second mission duration, and some of the RS-25 tests have run out to 720 seconds. However, some shuttle abort cases could run longer than that. A Space Shuttle main engine development engine ancestor of these RS-25s was hot-fired back in 1988 for over 2,000 seconds. As detailed in one of the NASA History Office publications, SP-4310, Way Station to Space, during the first shuttle return to flight after the Challenger disaster on the STS-51L launch, single-engine, long-duration life cycle tests reached 1,040 seconds in 1987 and 1988, and then a pair of tests that ran for 2,017 seconds were conducted weeks before the STS-26 return-to-flight launch. A few other news items to note in the past week or so. The Exploration Ground Systems Landing and Recovery Team returned to San Diego after completing Underway Recovery Test 11. This time they practiced recovery procedures for the upcoming Artemis II mission with the Artemis II flight crew. We'll be looking to get more details about how that went and any takeaways from the exercise. Reed Weissman, the commander of the crew, has been posting a weekly update. That's something worth checking out in the link on the screen. The Aerospace Safety Advisory Panel, or ASAP, held a public discussion following their first quarterly briefings with NASA officials this year. The ASAP is a federal advisory committee. After in-depth meetings with NASA, the public session gives them an opportunity to talk about initial impressions of the quarterly meetings. I'll come back to the Artemis-related notes of the meeting in a few minutes. Axiom Space posted a video about a NASA leadership visit to their work site. The promotional video shows a few glimpses of the lunar EVA suit they are working on for Artemis III, but not much else. For now, the latest is that the critical design review for the Artemis III lunar surface EVA suits is in August. The Human Landing System program posted a few pictures taken during testing of the docking adapter that SpaceX plans to fly on the Starship HLS version for Artemis missions. These pictures show a SpaceX implementation of an active adapter on top, approaching a NASA implementation of a passive adapter on the bottom. As far as I know, for Artemis III, Orion will be the active chaser vehicle for the proximity operations and docking segments, with Starship as the target vehicle, as specified in the HLS requirements. In that case, this configuration shown would be simulating something for Artemis IV and beyond, where Starship would be the active vehicle and dock to a passive adapter on the gateway for crew transfers to and from Orion. In the Artemis III concept of operations, both Orion and Starship would have active adapters, but Orion would be the side extending its soft capture system ring, and Starship would be the docking target in the passive configuration. Taking a look at the big picture for Artemis II and Artemis III, since those are the big items of interest right now, we're still looking for the next updates. For Artemis II, the ASAP provided a public summary of their private meetings with NASA. The panel is focusing on safety risks, not on milestones or schedules, and there wasn't much new to report on the big picture, other than underlining this issue with the Orion crew module side hatch. That would be one of those items to watch, but the schedule impact of that issue is unknown. Looking at this high-level list of long-term watch items, there hasn't been much to update here in the last couple of weeks. The visibility into the path from here to the next major milestone is still low. The note about the Orion vacuum test schedule was posted on February 13th. The statement about Core Stage 2 integrated functional testing and the updated ship forecast was supplied on February 15th, but no further clarifications the rest of February. I am hoping to get a little more info in March, but we'll see. One of those other things that might not be an obvious source of information is the annual release of the President's budget request. As noted in a previous video, we're looking for something extra in this fiscal year 2025 release, the cost and schedule baselines for HLS Option A and the Gateway co-manifested vehicle, the power and propulsion element and habitation and logistics module that will launch together, scheduled TBD. But the information in the detailed congressional justification document is valuable. It does get stale pretty quickly and is released only once a year, but it provides useful details and sometimes the only mention of some developments or efforts for the whole year. For Artemis III, I'm still trying to get updates on some of the missing puzzle pieces of Orion and SLS production. For example, the SRB motor segments were completed 2 years ago and are in storage, but what about the exit cones, or the forward assemblies and aft skirts and work at the KSC booster fabrication facility? Big picture aside from announcing that the Artemis III target date was pushed back from December 2025 to September 2026, not much else was disclosed with the delay. The next big Artemis III related news is still expected to be about Starship flight testing with IFT sometime in March. But the delay might not have a direct impact near term on Starship HLS development since they are already working overtime. The question of how the official delay affects the internal Orion and SLS milestones hasn't been addressed. So, for example, the need date for Core Stage 3 before the delay was somewhere around the end of this year or the beginning of 2025, and Boeing was pushing to get engine section hardware delivered from Michoud Assembly Facility to KSC. But what about now? It's likely that the need dates for Core Stage 3 and for Boeing's new final assembly facility in VAB High Bay 2 changed, but we don't know what they are. We could project some previous information if there's still a push to complete the Artemis III, Orion, and SLS hardware, but that's in question too, since there's a general expectation that even the September 2026 target date is still aspirational to some extent. So when will the Core Stage 3 boat tail assembly show up in Florida? And if not, is Boeing adjusting the short-term engine section integration plan back towards the first build model where the boat tail was attached late? And now that Artemis III is officially on the verge of fiscal year 2027 and probably moving into calendar year 2027, when would we expect to see all the Core Stage 3 hardware in the VAB for final assembly? Will that happen by the time that Artemis II is ready to launch? We'll see. And for now, we'll continue to watch and wait for updates.